Okay, Assalamualaikum and a very good morning, both of you. Okay, so today we are going to continue with different types of linear array antennas, such as the broadside, ordinary and fire, fish scanning, Hanson-Wood, yard and fire. But we are going to discuss only the first two, broadside and ordinary and fire. So the theta, the angle value stated is basically the intended maximum direction for each types of linear array antennas. Right, for broadside array antenna, it consists of number of identical parallel antennas arranged along a line, which are perpendicular to the line of array axis. Okay, for example, the array axis is here, so the antennas are oriented perpendicular. Okay, so perpendicular in this direction to the across the antenna axis, and the antennas are equally spaced, okay, separated by the same distance d across all elements, and all elements or each element is fed with current of equal magnitude and in phase. Right, so if this is the axis, for example y-axis, so the maximum radiation will occur normal to the axis, so in this direction. Okay, so the broadside array antenna intended or desire to have the maximum radiation at theta equal to 90 degree. So for example, here is theta equal to 0, so the maximum radiation desired is at theta equal to 90 degree. Okay, for example, in the right figure, so if the antenna is now oriented something like this, okay, separated by equal distance d. Alright, so this is the antenna axis z, so the maximum radiation is perpendicular to the axis, so this is the axis, so the maximum radiation towards y-axis. So you can see here the maximum radiation towards y-axis. Okay, and this is the 3D dimension, but it depends on the beta and the d as well. So if d is larger than lambda over 4 or larger than lambda over 2, then there will be modification or changes in the radiation pattern. Okay, so in some applications, okay, it is desirable to have the maximum radiation directed normal or perpendicular to the axis of the array. So for example, this is the axis of the array. Right, so the intended maximum direction is normal to the axis or in perpendicular in this direction. Okay, so it is at theta equal to 90 degree if compared to the axis at theta equal to 0 degree, and this can be achieved by exciting all elements with equal magnitude and in phase excitation. So there will be destructive fields accumulated, okay, along this axis, okay, contributed by each individual elements. Okay, for the broadside array antenna, since it is desirable to have the maximum radiation at 90 degree or perpendicular to the axis, therefore we need to ensure that the psi is equal to 0, and all elements is fed with equal magnitude and in phase, therefore there's no phase difference between the elements, and the psi should be 0 so that we can get the intended maximum or main beam towards 90 degree. And we need to ensure also the separation distance between the elements is not equal to multiple of lambda, and lambda n is the integer 1, 2, 3, and etc. We need to avoid d equal to multiple of lambda, because although the phase beta equal to 0, but when the separation distance between the elements is equal to multiple of lambda, the psi will be equal to 2 plus minus 2 pi n. So the maximum beam will appear at theta equal to 0 and or 180 degree, right? So you'll not as what we expect, the maximum radiation at theta equal to 90 degree. So therefore we need to ensure that when beta equal to 0, all antenna fed with equal magnitude and in phase. So the psi should be equal to 0. Okay, these two tables summarizes the mathematical expression in order to determine the position of nulls, maximum direction, so we can control the theta by having the d, okay, the d and the number of elements. And also table 6.2, we can also determine the first null beam width, half power beam width, and first side lobe beam width of the broadside array antenna. Okay, next is the ordinary end fire array antenna, in which it is more or less similar to the broadside array antenna. However, all elements are fed with current of unequal phase. Okay, it's the same magnitude, but with phase shift of 180 degree between the elements. For example, here if we excite the first dipole in this direction, so the second dipole will be excited in the other way around. So the same thing happened in the next element, right? So there's 180 degree phase difference between elements. So the elements are identical, fed with the same magnitude, but in out of phase, okay? And the direction of radiation for end fire array antenna coincide with the direction of the array axis. Okay, if this is the array axis, so the maximum radiation is along the array axis, okay, either in this side or on the other side. Okay, if compared to the broadside, so for broadside, the maximum radiation is perpendicular, okay, to the axis. So this is for broadside. Okay, so another example, if you have the antenna oriented along the z-axis, so this is your axis, so the maximum radiation occurs along the axis, okay, in this direction, okay, or at the bottom in this direction at theta equal to 0 or 180 degree. Okay, so for end fire antenna, the desirable maximum direction is either at theta equals 0 degree along the axis or at 180 degree, right? For example, if this is the axis, 0 degree, and here is 180 degree, so the antenna is oriented something like this. Okay, so the maximum radiation either in this direction or in this direction. Okay, so to control which direction, whether at 0 or 180 degree, so we need to control the beta. Alright, so the beta, if you want to get the maximum direction towards 0 degree, so the beta must be negative KD. Okay, remember for end fire, we have the element fed with out of phase, but equal magnitude. So for example here, you excite it on top, and this one the other way around. So to get 0 degree, we need to have the phase difference equal to minus KD. But if you want to get the maximum direction or main beam towards 180 degrees, so you need to have the beta equal to positive KD. Right, and the psi is equal to 0. Okay, table 6.3 and 6.4 summarizes expression, mathematical expression, in order to determine the position of the nulls, the maximum beam, half power points, final lobe, and etc. And for end fire, it also depends on the separation distance between the elements. If the d is less than lambda over 2, so you'll get the maximum direction in only one direction, theta equal to 0 or 180 degree. Right, for example here, these two, when d is less than lambda over 2, but then it depends on the beta, okay, whether it is positive or negative KD. Right, so it will determine whether it's 0 degree or 180 degree of maximum radiation direction. So if d is equal to lambda over 2, it has both direction, okay, meaning that you have both the radiation pattern, you have both the maximum 0 degree and 180 degree. While if the d is in between lambda over 2 and lambda, so you have in one direction and maximum towards two other directions. Okay, and the other one, if you have d equal to multiple of lambda, the end fire will have both directions and broadside. Okay, so this is when d equal to multiple of lambda, so n equal to 1, 2, and etc. Right, so if you have multiple of lambda, you will have both direction, so 1 and 2, and this one, and you have the broadside as well. Okay, next, the directivity of broadside array antenna. So the general equation for directivity is d naught equal to 4 pi u max over the radiated power. Right, so u max equal to 1, and for broadside, we know that the intended maximum direction is at theta equal to 90 degree. Right, so for d less than lambda, so the maximum directivity is equal to 2n number of element d, the elements passing, divided by lambda. Okay, and we can also use this equation, L equal to n minus 1 d, which L is the overall length of the array, overall array length. Okay, if the L is larger for larger structure of array, so the directivity is equal to, can be simplified to 2L over lambda. Okay, while for the end fire array antenna, so again it depends on D, so the array factor is given by this equation, so all equations will be provided during the exam or during the design. So, and the directivity of the end-fire antenna can be calculated by using this equation if the D is less than lambda. And you may also use this equation depending on the L, the length of the array structure. So you can use this one if you know the overall length of the structure. But for larger structure of end-fire array antenna, so you may use this simplified version for L, which it depends on the overall length of the end-fire array structure. Okay, let's look at an example. Given a linear broadside array of 10 isotropic elements, so meaning that you have your n equal to 10 separated by lambda over 4 between elements, so D equal to lambda over 4. So determine the directivity of the array. So you need to refer to the directivity equation of the array and make sure you determine the suitable equation depending on the separation distance. Right, so we have this equation. So for D less than a lambda, so you can use this one. Otherwise, for larger structure, you can use the other equations. So in this case, the D given, so D equal to lambda over 4, which is less than a lambda. Therefore, your D not equal to 2n multiply with D over lambda. So n is the number element, it's 10. So as usual, I always recommend you to write down the general equation first, then include in all values you have before you provide the final answer. So the D equal to lambda over 4 divided by lambda. So in this case, you should get 20 divided by 4 is 5. So directivity usually in dB, D naught equal to 10 log of 5. So it's 6.99 dB. Okay, let's have another example. Given a linear end-fire uniform array of 10 elements, okay, n equal to 10, with separation distance of lambda over 4 between elements, so D equal to lambda over 4. Again, more or less the same configuration as the broadside array, but you need to make sure you read it carefully because end-fire uniform will be using different equation if compared to broadside array. So you need to determine the directivity of the array. Alright, so for end-fire, so you have the 10 elements, 1, 2, up to 10, and this is the array axis. Right, so for end-fire uniform, you have the maximum radiation either at 0 degrees, towards 0 degree, or towards 180 degree. Or if you have the broadside, you have it perpendicular to the axis. Okay, so the separation distance between the elements D equal to lambda over 4. Alright, so to determine the end-fire uniform array directivity, so you need to refer to the correct equation of end-fire. And also it depends on the D. So for when D is less than a lambda, so you may determine the directivity by using this equation. Otherwise, you need to use this equation for larger structure. Alright, so in this case, D is given as D given equal to lambda over 4, which is lesser than a lambda. Therefore, you can straight away use this equation. So the directivity equal to 4n D over lambda. So for number of element 10, the D equal to lambda over 4 divided by lambda. 40, 4 is 10. So again in dB, D naught equal to 10 log of 10 equal to 10 dB. Thank you.